All right, everyone. So I want to do two examples that are continuing our work with arbitrary intervals. And the second of the two examples actually comes pretty much straight out of your homework assignment, homework number 7, problem 13. So for the first one, we have this function f of x is equal to 2 minus x squared. And for part A, we're going to find the net and the average rate of change of the function on the arbitrary interval from a to a plus h. So for the net change, we're going to want f of a plus h minus f of a. And as I've done before, I think we should start by finding f of a plus h separately. So again, we did this in the previous lesson. You'll notice that everywhere that f of x had an x, we replace with a plus h to find f of a plus h. Now, again, this might be a good time to pause the video to figure out the a plus h quantity squared. And then don't forget, you're subtracting a plus h quantity squared, so the negative has to distribute. So pause the video, work it out on your own, and then restart the video back up. So when we do a plus h quantity squared, we'll get a squared plus 2ah plus h squared. But of course, we're subtracting all of that. So the negative is going to distribute, and it'll be 2 minus a squared minus 2ah minus h squared. So be really careful with distributing that negative. For f of a, well, just everywhere we see an x, we write an a. So it'll be 2 minus a squared. So the net change, we're going to put these together. And again, pay attention to this negative, right? F of a is being subtracted. So again, might not be a bad point to pause the video, put together f of a plus h minus f of a, and see if it's worked out the way that it should, paying attention to those negatives. Okay, so here we go. So we have 2 minus a squared minus 2ah minus h squared. Notice no like terms here, but then we're subtracting 2 minus a squared. So the signs change, so it'll be minus 2 plus a squared. And here we do have like terms, the 2 and the minus 2, so those will reduce away. And then the negative a squared and the positive a squared. So those also reduce away. And all we're left with is negative 2ah minus h squared. So that's your net change. Notice, incidentally, that just like in the example we did with this in the previous lesson, the net change consists entirely of terms that have h's in them. So if you wanted, you could factor that h out. But I'm actually going to leave that for now. And we're going to move on to average rate of change. So remember, the average rate of change simply takes the net change and divides it by the length of the interval. So it'll be f of a plus h minus f of a all over a plus h minus a. Now, we just found f of a plus h minus f of a. That was our net change. Okay. And then a plus h minus a, well, that's just the length of the interval. That's h. And this is where the fact that everything in the net change had an h in it, every term had an h in it, becomes important because we can factor that h out, leaving us with negative 2a minus h. And now these two h's reduce away. So the average rate of change, after we simplify it all the way up, is just negative 2a minus h. So the net change is negative 2h minus h squared, and the average rate of change is negative 2a minus h. Now, for part B, I actually wanted to look at one reason that you might be interested in doing this work. So you'll remember that when we were finding the average rate of change on a fixed interval, you needed to know the endpoints, the value of the function at each endpoint, and so on. So either you needed a graph with some points labeled, or you'd have to do a lot of plugging in. In fact, in your homework number 7, that's precisely what you're doing. Here, though, I have an expression for the average rate of change of this function on any interval, where a is the starting point and h is the length of the interval. So look, I'm going to rewrite it here to have a little bit more room. In this example, a is negative 1, and a plus h is 3. So that means, since we're starting at negative 1 and we're ending at 3, h is the length of the interval, that's the number of units from beginning to end, and that's 4. So now that I know that a is negative 1 and h is 4, I can just plug that in to my expression for average rate of change. It's negative 2a, a here is negative 1, minus h, which is 4. So that's 2 minus 4, which is negative 2. So I don't have to plug negative 1 into the function, plug 3 into the function. I don't have to do any of that because my work in A expresses the average rate of change of this function on any interval in terms of A, which is where the interval begins, and h, which is how long the interval is. So let's look at this next example, which gives us a rational function. So with rational functions, kind of the elbow grease of the net change is a little bit more involved. Or it could translate into the elbow grease for average rate of change. There's just a little bit more elbow grease with rational functions. And in the next lesson, I actually talk some more about how we work with rational functions and average rate of change. And I have a handout for you that looks at this a little bit more in depth, maybe even more than your homework. All right, so we're going to look at the exact same two questions. We're going to find the net and average rate of change. So I'm just going to say find the net and ARC of G, right? So this is G of T on A to A plus H. So that's going to be our first. So we have G of A plus H minus G of A. Now, G of A plus H is there's not that much work to do here. Just everywhere that you have a T, we replace it with A plus H. So there is your net change, and you can either leave it this way and do the simplifying later, or you can simplify now by putting everything over a common denominator, and then some of your work is done for average rate of change. Based on how I do my next lesson, I'm actually going to go ahead and wait to simplify. So there is the net change, and now let's look at the average rate of change. So remember, the average rate of change, you have the net change, which is 5 over A plus H, minus 5 over A. So again, that's your G of A plus H minus G of A over the length of the interval. So what you have here is this kind of fraction within a fraction situation that's called a complex fraction. And it's pretty difficult to work with. It's pretty messy, so we're going to want to clear this out. So what I'm going to ask you, and again, this might not be a bad place to pause the video, kind of think about it and come back. Ignoring the denominator for just a second, what would you need to multiply the numerator by to get the denominators that are in the numerator to clear out? So pause the video, see if you can kind of figure it out. Okay. So what I hope that you remember from all of our conversations about rational equations and least common denominators is that a and a plus h have no common factors. So if you're going to reduce off or maybe clear out those two denominators, you need to multiply across the top by both a and a plus h. And you can't go multiplying the top of a rational expression by something without also multiplying the bottom, so that in the end, you are multiplying by 1. I'm going to erase this b here for a second to have a little bit more room. Now remember, and again, this takes us back to our work with rational equations and rational expressions in general, this a times a plus h needs to be distributed through. So check it out. When you do the first multiplication, the a plus h is reduced, leaving behind a. When you do the second multiplication, the a's reduce, leaving behind a plus h. And then on the bottom, while there's really no distributing, it's just h times a plus h, right? Okay, so now let's simplify, let's combine some like terms, let's see what happens. So pay attention to this negative here. So we have 5a minus 5a minus 5h all over ha times a plus h. Now look what happens. I'm going to use two different highlighter colors here. On top, you have the 5a and the 5a. So those guys cancel out, leaving you with negative 5h up on top. But now you have an h on top and an h on the bottom. So those reduce off also, leaving you with negative 5 over a times a plus h. So what we're seeing here is that the average rate of change of this function on any interval starting with a and ending with a plus h is negative 5 over the product of a and a plus h. So for b, let's use this work to find the average rate of change on the interval from 3 to 7. Okay? So notice here, you know what? I'm going to change the interval. Instead of 3 to 7, let's go 3 to 6, and you'll see why in a second. So notice that, again, the 3 is your a, the 6 is your a plus h. So you could say here that a is 3 and h is also 3 because there are 3 steps between 3 and 6. But you almost don't need that in this case because the average rate of change is just negative 5 divided by a times a plus h. So since you know a and you know a plus h, you don't really need to do anything else. So we have negative 5 over 3 times 6, which is 18. So I didn't need to plug anything in. I didn't need to do any fraction subtractions because once I've done the work of finding the average rate of change on the arbitrary interval, I can now find the average rate of change on any specific interval by just plugging in the values of a and h. So that's sort of the beauty of the arbitrary interval. It enables us to find average rates of change of the function on lots and lots of intervals very quickly, which can tell us a lot about the behavior of the function on those intervals, which is kind of cool. So in our next lesson, we're going to just round out this conversation about examples with rational functions, and that will pretty much conclude what we need to talk about with average rate of change. See you next time. Bye.